T be a linear operator. Okay, on V, linear operator on finite dimensional vector space V. Okay, suppose V is the direct sum of each T invariant subspace. Suppose V be a direct sum of non-zero invariant non-zero invariant subspace W1, W2 up to Wk. Okay, suppose V be a direct sum of non-zero invariant subspace W1, W2 up to Wk. That is, V is equal to direct sum of W1 plus W2 plus up to Wk, and P of Wi belongs to a subset of Wi. Okay, this is the definition of direct sum, and this is the definition of invariant subspace. Okay, for I is equal to 1 to k. I is equal to 1 to up to k. Okay, I is equal to 1 to k. Then subspace W1, W2, Wk are said to reduce T. Then the subspace W1, W2 up to Wk are said to reduce T or to form of T invariant to form T invariant sum decomposition, invariant direct sum of decomposition, to form T invariant direct sum of decomposition, direct sum of decomposition. Okay, V is the direct sum of W1, W2 up to Wk, and T of Wi is contained in Wi. Then the subspace W1, W2, Wk are said to reduce T. Okay, this is the definition of invariant direct sum decomposition. Decomposition means to separate it. Okay, or to form invariant direct sum of decomposition. Okay, furthermore, if Ti is the restriction of T on Wi, Ti is the restriction of T on Wi. Okay, Ti is the restriction of T on Wi. Why? Because Ti contained in Wi. Okay, so Ti is the restriction of T on Wi. Then T is said to be decomposable. Then T is said to be is said to be decomposable T is said to be decomposable into operator Ti. Into operators Ti. Okay. Then we say that T is said to be decomposable into operator Ti. Okay. A T is said to be direct sum of Ti, or T is said to be direct sum of Ti. That is direct sum of Ti's, and we write like this: T is equal to T1 of direct sum of T1, T2 plus up to Tk. Okay, so we can write like this: T is equal to T1 plus T2 up to Tk. That is, if the Ti is the restriction of T on Wi, then T is said to be direct sum of T. Okay, got it? So another point is that, next point is that primary decomposition theorem. This is the definition of invariant direct sum decomposition. Okay, now we see that what is the primary decomposition theorem. Okay. Primary decomposition theorem. Next point is that primary decomposition only statement is there. The proof is not required for you. Okay. Decomposition theorem. Very important theorem. Okay. Primary decomposition theorem. Statement. Let T be a linear operator on finite dimension vector space V. Let T be a finite dimensional vector space over. Let T be a linear operator. Linear operator on finite dimensional vector space V. Okay. T be a linear operator on a finite dimensional vector space V over F. Okay. Then let P be a minimal polynomial for T. Minimal polynomial for T. This P be a minimal polynomial for T. Okay. Then P is in the form of P1 raised to R1, P2 raised to R2 up to Pk raised to Rk. The minimal polynomial of T is in the form of P1 raised to R1, P2 raised to R2 up to Pk raised to R2, where Pi is monic irreducible polynomial. Okay, Pi is the distinct irreducible monic polynomial, where Pi is irreducible, distinct, different from each other. Okay, distinct irreducible monic polynomial. Monic means coefficient of each leading term is 1. Monic polynomial. Okay, each Pi is distinct from each other and which is irreducible monic polynomial over f. Okay, over f, and Ri is the positive integer. Ri is positive integer, not equal to 0 and non-negative. Okay, Ri is positive integer. Let Wi, okay, let Wi be the null space of Pi of t. Pi is the monic polynomial and Pi of t is the operator. Pi of t of raised to Ri. Okay, null space of this operator. This is the operator, na? Okay, Pi of t raised to Ri, which is nothing but operator. Okay, and let Wi be the null space, that is Wi is equal to null space of Pi of t raised to Ri. Okay, Pi of t raised to Ri. Then first condition, V is equal to direct sum of W1 plus W2 plus up to WK. Okay, V is the direct sum of all the subspaces. Second condition, each Wi is invariant under T. Each Wi is invariant under T. Invariant under T. This is the second statement. What is the third statement? If Ti is operator induced on Wi. If Ti is operator induced on Wi. Induced on Wi. Okay. Induced on Wi by T. Then minimal polynomial for Pi is Pi raised to Ri for I is equal to 1, 2, 2, 3. Okay, this is the statement of primary decomposition theorem. Okay, look at again. What is the definition? Primary decomposition theorem. Statement: let T be a linear operator on finite dimensional vector space V over F. Let P be a minimal polynomial for T, okay, which is in the form of P is equal to P1 raised to R1, P2 raised to R2 up to Pk raised to Rk. Okay, where each Pi is distinct, irreducible monic polynomial over F. Okay, and Ri is positive integer. Okay, then and let W be the null space of Pi of t of Ri. Okay, Pi is the monic polynomial. Okay, irreducible monic polynomial, and then Pi of t raised to Ri is operator. Okay, this Wi is the null space of Pi of t raised to Ri. That is, W is equal to null space of Pi of t raised to Ri. Then all these three statements are hold. What are these three statements? V is equal to direct sum of W1, W2 up to Wk. Second, each Wi is invariant under T. And third, if Ti is operator induced on Wi, okay, restriction of T on Wi by T, then minimal polynomial for this Ti, okay, minimal polynomial for this Ti is equal to Pi raised to Ri. Okay, for T1 this is the minimal polynomial, for T2 this is the minimal polynomial, for Tk this is the minimal polynomial. This is the primary decomposition theorem. Okay, the statement is only in the syllabus. The proof is not required for us. Okay, so here we completed the second chapter, elementary canonical form. So in the next video we will see the chapter number 3, Jacobian and rational form. Okay, thank you.